In today's video, we shall have a closer look at projectile motion. Projectile motion is a two-dimensional motion in gravity. What that means is, if you were to throw an object with some speed at some angle, say from the ground, it will follow the following trajectory. So that is a projectile motion. The shape of this trajectory is a parabola. Let's see why that is the case. To understand this, let's imagine you have a cart, and this cart is moving to the right with some constant velocity, say u. When the cart is here, someone in that cart throw an object upright like that. And as the cart moves, say, to this location, what would the trajectory of this object look like to a person standing outside? Say that at this location, the object lands back to the cart. So that means to the person outside, the object would have traveled in this manner. So that is the basis of projectile motion. Another thing to note, to this person, the initial launch speed of that object would be in that direction. So that is the initial velocity of this object according to the person outside. So let's analyze that projectile motion. You have an object that's being launched in that direction. Let's say the projection angle is alpha and the initial velocity is u. The trajectory will be something like that. Let's analyze this trajectory closer. We are going to take that to be the y-axis, that to be the x-axis. So the x-axis coincides with the ground. This is a motion in gravity, which means gravity acts only vertically downward. That is the only direction for the acceleration of this object. So at any point along that trajectory, this object would be accelerating vertically downward. The acceleration is given by minus g, j hat. There is no acceleration along the x direction. So we say the y component of the acceleration is minus g, the x component of the acceleration is 0. So that means we have kinematics. Let's look at the x motion, or the motion along the x-axis. Now we know that the initial x component velocity is u cosine alpha. Likewise, the initial y component velocity is u sine alpha. This follows directly from trigonometry. Because there is no acceleration along the x-axis, the later x component velocity will always be ux, namely u cosine alpha. So that means the x-coordinate would vary quite simply as vxt, or ut cosine alpha. So that is the kinematics equation along the x-axis. Let's call this equation 1. Now let's look at the y direction. Because the object is constantly being pulled downward, the y component of the velocity of this object would change from this to some other number, and it's given by kinematics. It is uy minus gt. Uy is u sine alpha minus gt. It came from the kinematics equation u plus at, where acceleration is minus g here. So that is equation 2. The final equation is the change in the y-coordinate of the object as it moves, and that is given by half at squared plus ut plus y naught. That is the second equation of kinematics. So y equals minus half gt squared, because a is minus g, plus uy. Uy is u sine alpha. Don't forget the t, plus y naught. Y naught is the initial y coordinate of the object because the object starts here it is quite simply 0. So that is equation 3. Let's see what kind of trajectory this is. We know it's a parabola, so let's show that to be the case. To do that, we have to express t in terms of x from equation 1, that is just x over u cosine alpha from that equation, and substitute this t inside here and there for the equation for y. Let's see what we get. Y equals minus half g t squared, so t squared is x squared, over u squared cosine squared alpha, plus t is again x over u cosine alpha times sine alpha. Let's simplify this. This goes away, so that's going to give you x tangent alpha, sine over cosine is tangent, minus now the first term, which is g over 2 x squared over u squared cosine squared alpha. Upon inspection, this equation has the following form. Y equals to x, a constant, let's call it a, plus or minus, let's stick with the minus, x squared. All the rest are just constants, let's call that b. This is an equation for parabola. So now we have a clear idea that the trajectory that this object follows is clearly a parabola. Next, let's proceed to calculate this distance. This is known as the range of that flight. It is the distance from the takeoff point to where it hits. At the point where it hits the ground, the y-coordinate is 0. So setting y equals to 0 here, we get 0 equals, let's take the x out, tangent alpha minus g over 2 x over u squared cosine squared alpha. So the value of x when y is 0 is the range. One solution is, of course, x equals to 0. That corresponds to that point. We are not interested in that point. So let's look at the terms in the bracket. So if that term goes to 0, that means tangent alpha equals g over 2 u squared cosine squared alpha x. This is the range that we are interested in. So let's rewrite that x as the range r, and you can solve for r. Solving for r, you get 2u squared cosine squared alpha tangent alpha over g, which can be simplified to u squared over g times sine 2 alpha. Another point of interest is the maximum height the object reaches in its flight. In order to determine that value for the maximum height, let's go back to the parabola equation that we wrote down a few minutes ago, which is the following. U squared cosine squared alpha x squared. This parabolic trajectory is symmetrical about that maximum height. So that means this distance here is the range divided by 2. And that is the balance, range divided by 2. What that means is when y equals to hx is r over 2. So substituting that information in here, we get g over u squared cosine squared alpha r squared over 4. We have already determined r in terms of the other constants over there. Substituting that r in here and simplifying, you will get the following for the maximum height, which is u squared sine squared alpha over 2 times gravitational acceleration. It is just a matter of algebra to go from here to there. We urge you to give it a shot. So there we have it. 2 important results in projectile motion, one for the maximum height, the other one for the range. We stress here that these 2 equations will only work when the takeoff point and the landing point are at the same level. So let's see how to use those equations by looking at the following problem. a rock is thrown with an initial speed of 20 meters per second, if it's launched at an angle of 40 degrees above the horizontal, what is its horizontal range? So it will go and hit back the ground. So the takeoff point and the hitting point, the final point, are on the same level. So let's calculate the range. We know the equation for the range is given by u squared over g sine 2 alpha. In this case, u is 20, so 20 squared over g. We know g is 9.81. Sine 2 alpha. Alpha is 40, so 2 times 40, that's 80 degrees. And the answer is about 40.2 meters. Let's go ahead and calculate the maximum height h. The maximum height is given by the following equation. U squared times sine squared alpha over 2 times gravity. So u is again 20, so 20 squared. Sine square alpha, alpha is 40 degrees, over 2 times 9.81, and you're going to get about 8.4 meters. We again stress that these two equations for the maximum height and range respectively will only work when the takeoff point and the landing point are exactly on the same level. As always, thank you for watching.